Okay, let's start. Mm. So in this tutorial, we are going to talk about modeling and control of multirotors. It's targeted toward multirotors, not on fixed wings and other types of aerial vehicles that we usually use. I tried to be to be giving a very good overview of what control system and multirotors are, not going too much into like very technical details. But I tried to take a practical approach. So I hope this will be very helpful to at least know what it is and know where to look and understand the terminology. So what is control? Well, it's usually an attempt to make the robot do what we are asking it to do. It's usually, for many people in robotics, it's just some magic box that we ask it to, okay, make the robot fly. It just makes it fly. This is exactly what we call it, from a desire to action. This part of the robot is what makes it happen. And the Wikipedia has the worst definition of it. It doesn't have a good definition. It says the objective is to develop a control model for controlling systems using a control action and ensuring control stability. That's the definition of a control system. So, but intuitively, all of us know what it means. So that's good. If we look at a drone from very high above, bird's eye view, we have this computer or remote controller that sends some commands to our drone. This drone has, well, its own dynamics, its own motors and stuff, but what controls it is the controller, and what measures what is happening is the perception system. The robot also interacts with environment. So you know that perception system is so many different things: computer vision, like all kinds of sensors, and like lots of things from SLAM and cameras. The same way, controller system is also a very, very large thing that we just will try to break it down here. Like on day one, it was my own question: isn't it the solved problem? Like we know that robots can fly now. What is there to do? For many applications, usual applications, yes. Like if you just want normal movement within the defined range that you can see the robots fly, yes, that's a solved problem. Like DJI comes with a decent controller. There are many open source controllers like PX4. Basically, they are flight stacks. But you still need to understand what controller is, even if you're not exactly dealing directly with controller, because you need to tune your like your parameters in order to get a better performance. If you want to follow some trajectory for your SLAM, you need to follow it well. So you need to understand what's there to tune. What are the parameters? What does it mean? Also, if you're coming up with new applications, if you want to do more stuff, not just normal flight, you do need to implement new controllers. It can be like, to be more agile, for example, if we want the multirotors someday join our life, fly among us, they need to be able to fly fast among obstacles, react to dynamic obstacles, react to sudden changes in the environment. Or if they want to carry cargo, for example, if you've probably seen some helicopters that have some large cargo on a rope below them. That usually has a very, very good pilot who has learned how to do that. So if we want to make this stuff autonomous on multirotors, we need good controllers to develop. Or if we want to interact with environments, for example, if we want to measure stuff, or if on the wall, or for example, if we are inspecting the bridge, we want to check if one place has good coating, or if we want to play ping pong, buy a drone that plays ping pong for with us. So all of this needs controllers, different controllers than normal ones that you have in commercial packages. Or at all, if we want new designs for new applications, like for flying cabs, we do need to implement new controllers. So it's not a solved problem at all. I'd like to show you some like 5-second examples, like what I mean. For example, you can see a suspended load from this multirotor. It actually uses its own dynamics, like it goes back and forth. So the load is faster than it is, so it can actually pass the load through the obstacle. This one cannot go straight through that obstacle. It needs to tilt in order to pass through it. This one does flips. I'm not exactly sure what would be application, but it's cool. And this one tries to interact with the environment. I'm not sure about the quality of the videos that you're getting. I hope it's decent enough. So let's go about modeling. What is modeling? Well, we have so many different types of quadrotors, like from auto to DJI. Each of them has a different mass, different inertia, different behavior, different motor, and different sensor data. So we need to model what our drone has mathematically in order to understand it. Or for even other designs, like some weird designs that recently have popped up with tilted rotors and like a dragon shape for different applications. So we need to be able to mathematically understand them. The reason is that what is modeling? First, I said it's a mathematical formulation of what the robot is, how the robot behaves. And for us, flying robots, their behavior is captured by their motion. So for us, it's a mathematical estimation of how their motion is. Usually, we break it into kinematics and dynamics. Kinematics is modeling the motion without considering the forces. We consider how the robot moves with, like, for example, if we are flying, what's the if we know how what's our position? Do we know the position of each of the rotors in order to calculate our thrust? Dynamics is the motion that is caused by the forces. So if we are generating some thrust, how is the robot going to accelerate? Basically, our Newton first, second, and third Newton laws. So why do even we do need to model it? For very, very simple applications, probably you don't need to even think about modeling. But in general, in order to control it well, we need to at least have some understanding, some level of modeling how it is. Even if you say it's a point mass, you're still modeling it. So in order to control it, in order to understand what's the operational limit, like what's the maximum acceleration, what's the maximum speed, what's the relationship between like angular acceleration and our speed. And in order to improve our design, so if we don't model it, how are we going to quantify the design? How are we going to understand how we can improve it? And in order to solve the issues with mostly controlling it. So we know probably nothing is perfect in the world. So the same is for the multirotors. There is no perfect model. But the simplest, you can just probably assume that it's a point mass. But if you assume it's a point mass, you can't deal with the rotations. Some other common way is to modeling as a second order system. But usually it's more complex than that. But we always try to not go super complex with our model. We can always add drag, lots of other low order effects, and make a very large mathematical formula that gets pretty close to the actual multirotor. But because of all the uncertainties that exist in the world, lower order effects usually don't have that much effect. That's why they are called lower order. So usually a simple gust will change the behavior way more than like considering lots of those effects. As a result, we try to not not go too complex with the modeling. One way of estimating the model without trying to do lots of mathematical thinking is to perform system identification. So we have the input data, we have the output data. Can we estimate what's that function in between this input and output? Just mathematical function. So if we estimate the mathematical function out of it, we have the model of the system. It's pretty much like machine learning. Actually, these two are interchangeably used. And you still need some initial guess about the model in order to be able to like estimate. You need to know, for example, it's a second order model. And then you estimate the parameters. And in order to collect that input output data, you still need a good model that works well enough that your robot flies. So you can collect input output data. Otherwise, if it's not flying, how are you going to collect that? And why do we have so many different models? Why don't we just cite one single paper from 1990s that has solved all the models? Well, one reason is that new applications model new effects that are not modeled for normal applications. And as I mentioned, we always try to go as simple as possible in modeling, as simple as it's needed for our purpose. Multirotor dynamics in general is super nonlinear. So, and it's very complex. So if we don't want to choose the simplest, we can just go to the rabbit hole. Also, like what are, depending on the sensor data that we have, we can, our model can change. Do we get roll pitch yaw, or do we like measure rotation directly, or is it angular velocity directly? So what is it? What's our model? And so different models tend to capture the operation in some certain area. Sometimes we need several models for different operation regions. For example, for flipped multirotor, we may need a different model than straight up multirotor. As a result, if you're trying to make it flip, it needs to switch the models in between. And we need a model that goes well with our controller, depending on what type of controller we are willing to write. Usually we tend to go with the simplest that works. So then we would need a model that goes with that controller. An example of kinematics, as I mentioned, is it's all the motions that are not considering the force directly. So first we need to define what are our frames. We have the inertial frame that we usually just assume that it's the 0, 0, 0 is where we are taking off. We are assuming that Earth is flat, and we are assuming at the same time that Earth is a perfect sphere for the gravity. So lots of assumptions just to define our frames, but the most common way of it is to go with north-east down. So we assume X direction is north, Y direction is east, and D direction is down, or ENU, you can figure out what it means. And we also need a frame on the robot. We usually go with forward, right, down. We need frames to be defined under rotors, so we can convert all those forces generated by the rotors to the world, to inertial frame through the body fix. Usually the way that we define is we define rotor frames with respect to body and body with respect to inertial. So we can go with two-tier calculation. We can reach from rotors to inertial. We also need to define the relations between the frames. As I mentioned, we need to know how we can convert them. And we need to, if there are other things that, depending on our data we need to also define those for our kinematics. So you will see lots of different kinematics for many different, in different papers. Usually there is no consensus on what even your inertial frame would be. Like this, as simple as that. Some people go with northeast down, some northeast north up, and some I've seen even northeast up, which is not even right-handed coordinate frame. By the way, whenever you have any questions, just jump in. So with dynamics, we need to decide on our formulas. Are we going with Newton-Euler? Are we going with Lagrange? What kind of dynamics we are going to use? There are different ones. The most famous that we had in our high school physics books is Newton-Euler. Force is the multiplication of mass with acceleration, and the same we can calculate the moments. So now you need to define what are the forces in our system in order to be able to calculate your acceleration. If you have, for example, 4 rotors, your forces are the result of those rotors rotating. So your global forces will be the sum of the 4 generated thrusts converted from their rotor frames to the body frame, from the body frame to the world frame, and then combined. And the same goes with the moments. So after we do this, are we done? Can we go home? No. yeah, lots of papers still tend to do to model their motors. Usually we just buy motors, good motors that already have ESCs, that already, the motors are already controlled. We just send a PWM signal and it does the job for us. But for many applications, people tend to control the motors themselves. They are not satisfied with commercial controllers, or they just buy the cheapest motors that don't have commercial controllers. So you will see in many papers just trying to model the motor as well. But we're not going there. And there are many other effects that, in what I mentioned, are not modeled, but we, depending on the application, we should model. If we are flying in high wind, probably you need to consider the effect of the wind. Like, you need to know that the drag effect depends on your speed, and like what are the forces that will be put on your drone, and all that goes into that F equals M acceleration. And so there are also limits that we need to understand and define. We need to know what's the maximum speed of our drone, what's the maximum tilt that we are allowing our drone, what's the acceleration, and all of these need to be defined. So let's go to the controller architecture. Up until now, it was this magical box with some input and some output that does the control job for us. So that some input is usually the command that we are asking the drone to follow. Like, for example, we're asking it, okay, please follow this, go to this point. And the current state is, and also another input is the current state, is that where are we right now? So the controller can decide which direction to go. After deciding it, it just outputs the command. In Multirotor, the commands are usually what we are dealing with as a whole is the motor commands. So it generates at the end either PWM or like the speed of each rotor. And as a state here, we mean at least position, roll pitch yaw, their derivatives, first and second derivatives, are our desired state that are used in different levels of multirotor controller. So what are the main components? Each person technically can define their own architecture as long as the input and output is the same. Nobody cares what's inside if it's working well. But there are some standard components that usually are used in multirotors. If you're working with DJI, if you're working with PX4, autopilot, all of these have these components. One is trajectory controller, that if you want to follow a desired trajectory, that's your boy. Another is position controller, that goes to a point that we commanded. Attitude controller controls the roll pitch yaw, the tilt of our drone. Rate controller controls the angular rates, so how fast we are changing the roll pitch yaw. Control allocation, you might have not heard of it. It basically gets the output of those parts and converts them to motor commands. So like, it can accept accelerations and angular accelerations and convert them to motor commands. We will talk about all of these components quickly after this. So also you may see like velocity controller, acceleration controller, or as I mentioned, motor controllers. These are all out there. Really depends on what architecture that specific drone has. not not every architecture has all of the mentioned components. Some of them are missing in some of them. For example, uh, like you may not have velocity controller in your drone, or you may not have acceleration controller. And some of them can be combined into two. For example, in PX4, you will see rate controller is inside attitude controller. So basically, the whole thing can be called attitude controller. Or some people have recently, especially in Berkeley area, has started just not caring about controller, and like they do end-to-end reinforcement learning. So you get the input, you get the output. They don't care how it happens. It doesn't work yet, but maybe in the future we will have that. And we can have just one magical box, but in practice, for us, it's always, for designers, it's always easier to create like some hierarchical architecture, break it into different parts so we can deal with them, we can understand what is happening inside. So this is an example architecture from PX4. This is, so I didn't put the trajectory controller. Usually it's not inside. If you give X, Y, Z and yaw commands, the position controller, what it does in PX4, it calculates what attitude we need in order to go toward that position. And what is the, like, what are the forces that we need to generate, like the rotors need to generate. Then attitude controller computes the, takes the attitude, computes how much the attitude needs to change, technically calculates the rates, and the rate controller takes the rate, calculates the rate angular accelerations, and control allocation takes all and just does some mathematical job and gives the command to the multirotor. So let's talk what are the different types of methods. I'm not talking about the exact methods. I'm talking about different types of methods that you will see out there. You will, when you're talking with multirotor people, you will see, you will hear a lot of this terminology. You need to know, like one way of classifying the controllers is open loop versus feedback controller. Or you can talk about linear or non-linear controllers. Non-linear controllers on their own can be adaptive, optimal, or robust, or lots of other things, or even combined, like it can be robust adaptive control. Or it can be univariable or multivariable. It means that, is it just taking, for example, yaw and tries to control yaw, or can it actually take 10 different things, calculate something, and give a command that does a decent job with all 10 different things? The geometric control is an attempt to remove some dependencies on our coordinate systems. So these are different classifications. They can be mixed. It can be like nonlinear adaptive, nonlinear adaptive multivariable controller, for example. In order to choose the right method for each parts of our controller, you need to know what's your objective. Like, are you trying to have an optimal result, or are you trying to increase the execution speed, or do you want to estimate some parameters and make it adaptive, or do you want to make it as simple as possible? For today, we will work on the simplest ones. And of course, simplicity is very important again. Like, we should go as simple as it works. What is the role of the controller in general? Like, for example, if rate controller doesn't do the best possible job and like outputs something that is not the best, can it rely on other controllers to fix it, its error? For example, if the position controller is not very well tuned, can it rely on attitude controller? How much can it rely on attitude controller to fix its problems? And like how fast how many times per second our controller is going to run? That defines what kind of control method we can use. And what are the limits that we are putting on the controller? So the common controller methods in our UAVs, like we do use open loop controller, you will see where. PID is by far the most common controller that you will see in multirotors. We'll talk about it later. You will see LQR controllers trying to define some cost for it, H-infinity methods that try to make a robust flight. And feedback linearization is very common, especially for some more weird architectures. Geometric controller has recently gained some attention. Backstepping tries to not linearize anything. All of the above in some way try to linearize something. Backstepping tries to not linearize anything and tries to solve it as a nonlinear system. And learning recently, machine learning is gaining some attention in the field of control of multirotors. So let's talk about the components. The PX4 components will start from the end to the start. As I said, control allocation is basically a mathematical formulation. It is usually open loop because it takes the input, it gives the output, it doesn't care if the output worked or not. It will wait for the next input. So it doesn't go and correct like if the result is not good. So basically, in many cases, it's just a mathematical function. It's not even a controller in that sense. But the most common type of it is control allocation matrix. It's just a matrix that takes the input, multiplies by it, consider it completely linear, and outputs the rotor commands. There are lots of problems with it, but you can see all of these robots flying, so apparently works. Dynamic inversion is trying to, after modeling the drone, inverse that modeling. And for example, if you want the drone to have some acceleration, in this way, your input to that will be that acceleration. It calculates, because it's the inversion of our model, it will actually, instead of taking the motor speeds and giving acceleration, it takes the acceleration and gives you the motor speeds. So it makes the life a bit easy in that sense, but there are some problems with that as well. So rate controller, it takes angular velocity and outputs angular acceleration. And usually it's a simple PID controller. In PX4, it's a PID controller. And it needs a very high rate feedback loop. It needs to be executed at least 500 times per second in order to be able to control the multirotor well. So in PX4, currently, I think it's 1 kilohertz, the default. So the same with attitude controller, you take the input, roll pitch yaw, or it can be getting rotation matrix, or quaternion is also very common. In PX4, the input is quaternion technically, and the output is our rate, is angular velocity. In PX4, it's just PID. It's very common to design it as PD, like setting the I as 0. There are cases that they design geometric controllers or just do system identification. That's also very common, or backstepping. But by far the most common is just PID. It requires a high rate feedback loop, not as high rate as the nested rate controller, but still very high. In Pixel, it's still that same 1 kilohertz. Position controller takes the position, obviously, and it does two different things. The PID loop of it, or if it's not a loop, one of the outputs calculates the desired forces that it needs. It can be that force, when we say forces of the robot, it means technically acceleration of the robot. So it calculates the acceleration of the robot. Usually it's P controller, or like the PID is too sophisticated usually for that. But P controllers mostly works depending on your modeling. And it needs way lower loop. Even 50 hertz usually works well, depending on your application, how close, how much you want to reduce the error, the tracking error. 50 hertz can work. And because of this lower loop rate, it can be moved out of the autopilot to the onboard computer. So usually that connection between onboard computer and the autopilot is a bottleneck for our rate. So we cannot have 1 kilohertz if it's on onboard computer. I mean, our connections don't support that. So usually it's around like 50 hertz if it's on onboard computer. The other thing that it does some mathematical calculation, not control thing. Mathematical calculation to see that in order to achieve that acceleration that we need in inertial frame, if we want to go 2 meters per square second forward, what should be our orientation? What should be our roll pitch yaw? We definitely need to roll forward if we want to go forward with 2 meters per square second. How do we calculate that? And last of all, trajectory controller. It's usually on the ground station or on the onboard computer. It can be just replaced with a remote controller, a person who is just sending commands using his remote controller. Normally we have some objective to achieve, but the simplest form is just a loop that sends the next waypoint. We have a bunch of waypoints called trajectory. It sends that it says, okay, go to 0, 0, 0. Oh, you're there. Okay, now go to 2, 0, 0. Now go to 3, 0, 0. So just a loop that checks if you have reached that position, go to the next. But more sophisticated of that is like, oh, so you are going to reach it with this speed. That speed needs this much turn. In order to turn to the next point, you need to like start decelerating or start giving command to another direction. So it can become very sophisticated to optimize time or minimize the tracking error, depends on the application. So let's very shortly talk about PID controllers because we're going to implement it. It's the most common type of controller. has three main parameters: the proportional gain, the integral gain, and derivative gain. You will see lots of places that one or two of these gains are zero, in which case, if, for example, your integral gain is zero, you only have P and D, it's called proportional derivative. Or like, if both of them are zero, you just have proportional term, it's called proportional controller. The output of PID controllers, it was a bit confusing for me the first couple of years. It can be interpreted either as your first or second derivative of the input. Like if you are controlling position with a PID, the output, you can interpret it as a velocity command or as an acceleration command. It's your choice. And it's a linear method, but works for many nonlinear systems. And we usually try to linearize the systems by breaking them down into smaller components or into smaller regions of operation, so we can use PID on them. In its purest form, it's just a multiplication of some gains by some errors, and it doesn't respect any physical limits. If your, for example, output is acceleration, it can give a very huge acceleration that the robot cannot achieve. So in its purest form, it doesn't respect any limits. You can see the design of it. So the first, what you do is you have a desired behavior R, for example. You want to go to 10 degrees of yaw. So R would be 10 degrees of yaw. And you have this measurement from the robot, Y of T. So current yaw, for example, it's 2 degrees. You calculate the error, which would be 8 degrees, and use the PID gains to calculate that. Since it's a linear method, and since like derivative is a linear method, the derivative of your error, I mean technically E dot, is the error of your derivative. Like the derivative of your position error, it's the velocity error. So if you have velocity, for example, for position controller, if you have velocity, you know that your error is the velocity error. The same with integral. It's very simple. If you've never done it, you will enjoy. So there are some consideration, as I mentioned. The output is unbounded. You do need to limit it if you need to. If you want to have a decent PID controller, you need to limit the output. For example, you can limit the acceleration. And some other limits in your work are not considered with PID controller. For example, if you are taking position and outputting acceleration, you're not considering, even if you put maximum on your acceleration, you're not putting any maximum on your speed. But in actual world, your robot also has maximum speed. So you can also limit that in some ways. If you are using integral term, it's just an integration of your error during time. So if you have very large changes in command, for example, if from 50 degrees yaw, you are going to minus 80 degrees yaw, next command is like go to minus 80 degrees. During this change, the accumulation of your error is very large. So as a result, the next time that you are changing your yaw, you have a very large error in I that needs to be dealt with. Otherwise, it will not let you go to the new point. It's called integrator windup. You need to handle it. The system is non-linear, but we are using this very simple linear method. So when you're tuning the system, you should not really expect exactly what you think it should do. You will see very sudden changes in the behavior of the system, just by very small change in the tuning. And tuning one module can depend on other modules as well. Like the position controller tuning can depend on the tuning of the like other parts of the system, like attitude controller. But that's not just PID in general. So we talked about normal drones. Like most of you have only seen normal drones that we call them underactuated. They have, like quadrotors, for example, have only 4 rotors, but they are flying in a 6 degree of freedom space. And 6-dimensional space means 3 degrees, like 3 dimensions of space, X, Y, Z, and 3 dimensions of rotation, like roll, pitch, yaw. And so we have this 6-dimensional space, but we only have 4 actuators. So it means that we only have 4 degrees of freedom. Even if you increase that number of the rotors, we will see that because all our rotors are on the same plane, it doesn't add to the degrees of freedom. And as a result of that underactuation, you see that if you want to go forward, for example, you need to tilt forward. You cannot just tilt backward and go forward. Yeah, so it means that your roll and pitch is not independent of your movement, of your acceleration. Your roll and pitch do depend on your acceleration, and that's the problem in underactuation. It's not suitable for all applications. It's suitable for many of the applications that are currently drones are used for. But if we solve that problem, we can imagine lots of new other applications. So in order to achieve that, we can make some structural changes. It can be either modifying our available underactuated structures, like tilting the motors, the rotors, so they're not coplanar anymore, or completely design something new from scratch. In this picture, for example, you see like this dragon is complete new design from scratch, or even this lower left one is a complete new design from scratch. This one is a complete new design from scratch, but this one is just a modification. In this one we just tilted the rotor of a normal hexarotor, and we achieved full actuation. So there are some problems with fully actuated UAVs. First of all, we need 6 actuators. We cannot achieve 6 degrees of freedom with less than 6 actuators. Lots of those in those pictures, lots of the designs that you saw have way more than 6 actually. Like some of them have 12. And it means that more energy consumption, and because we tilt, for example, we tilt our rotors, we lose some of the efficiency just because of the direction of the generated thrust. So we have some energy issues with fully actuated robots that is still not completely solved, and probably we are waiting for better batteries to be invented. But another issue is that we need new controllers because it's a new design. So we cannot just directly use the normal controllers that are optimized for underactuated robots to this. But there are good things about it. Like we don't need a gimbal, for example, anymore. We can choose the angle of the desired angle of our camera just by our own tilt. We don't need multi degrees of freedom arm for physical interaction. We can choose that end effectors pose just by our own tilt. It has a better control over the end effectors pose as a result, because gimbals and like another arm are usually slow to react. You need to calculate, okay, what should be their reaction now, what is the reaction. They measure what the drone is doing, drone is measuring what they are doing, just to calculate what would be. So there is always a delay. The cameras, for example, in cinematography, for that, the camera on the gimbal, if you don't consider the post-processing, will be more shaky than the one on the well-tuned robot. And it opens a new possibility for us. It allows new interactions with the world. It allows lots of new applications that we could not imagine before. So let's talk about the code that we have. In this code, it's a MATLAB code. You can get it from this Bitbucket. As a reminder, if you have downloaded it before, please git pull so you get the latest changes. I changed it 2 minutes before starting the presentation the last time, so please pull the changes. I have written it on MATLAB 2019B, but I'm sure it will work on 19A and probably 18, I'm not sure. I'm pretty sure it won't work with 16 and older. So I hope you have that newer MATLABs. There are 3 different tasks in it. We will go through them together. I'll open the tutorial here. First is tuning the PID for attitude controller. So just to learn how the system responds to our stuff, how is the reaction of our system to different tunings, how are we going to hit the limit, how are we going to choose the gains. After that, let's write a new PID controller to calculate the acceleration for position control. And let's see how we can calculate that attitude in the position control, that desired attitude that we are sending to attitude controller from our acceleration that we just calculated. And at the end, we are going to actually model a fully actuated robot and try to fly it to some position. So if you have any questions, I'm at your service. After that, we can start the code.
Hey, I have a question.
Sure.
So being fully actuated does not imply that it can hover at any orientation?
So hovering at any orientation means we call it omnidirectional. Fully actuated means that at least around our operating point, we have full actuation. We can control our roll pitch yaw and XYZ completely independently. So we can achieve any orientation around our operating point, but probably we cannot fly with 90 degrees. So let me, so for example, in these these ones. So you can see this is fully actuated, the right top right one. It's from ETH. It's called Bolero. It is also omnidirectional, but it's also fully actuated, and it can actually fly at any orientation. But the one that we are using here, this is our design at CMU for a very similar task. I assume that much tilt we can do. Like I have been able to tilt it up to like 30 degrees, fully having control over its roll and pitch and yaw. But more than that, well, because our tilt is fixed, you will lose you will not have enough vertical acceleration in order to come over the gravity. So it will fall. So you cannot completely go 90 degrees with this lower model, but with this you can.
But is it just a matter of thrust? Because you sent me a paper that said you need 7 thrusters.
Yes. So no. In order
so
to
it's
make
more
it
than just thrust.
Yeah, in order to make it omnidirectional, you need that 7 thrust.
Okay.
But for full actuation, 6 works.
Gotcha. Thank you.
Sure. So there are 3 different tasks here, as I mentioned. The files are called task 1, task 2, and task 3 MLX. These are live MATLAB codes. There are lots of there's lots of description before each command that is here. You will be able to start the simulator to define your multirotor, like control enter. When you use control enter, it runs that single section. For example, if I run it like here, I'm defining this. So as you can see, when I ran this, I have this multirotor defined. You can actually go into Multirotor and see all of its properties. Let me visualize it. For example, when you run, it paints what you have actually done here. Let me take it out. So I'm not sure if you are able to see this new figure. No? Yes? Okay, so anyway, if you open it in 3D, you can actually check the figure in 3D. You can change the definition if you want. Like instead of 45 degrees, you can like just have one of them at 0. I don't know how to move this. Okay. How many I open? Yeah, so for example, if we define the rotor placements as this and then visualize it, you will see it will look different. But it depends how you want to define your multirotor. Then you can read about the controller. You can everything we talked here, and you can define the controller, define the simulator, and start tuning it. So the default tuning is like just P and D gains as 1 and 1. You will not see a very good design response. I ran it, so you can see how it can track the desired roll, pitch, and yaw. You can try to make it better, and the task is tuning it. I think like 15 minutes should be fine for this. And if you have a question, I'm right here.
Hey, Azarakhsh.
Yep.
I suppose for task one, the default settings is not good enough, so we have to tune it.
Yes.
Can you give us a, I mean, what's the target performance we should get after retuning?
So I have explained it in there. You will see the desired response is to reduce the overshoot and to reduce the times. Like settling time can be a good indicator of that. Like I was able to achieve 1 second, 1 point something at most.
Okay, thanks.
Even more important than achieving the best time, it is for you to actually learn how to achieve that. Like I have written it there. I'm not sure if it's clear. You can start with P. You will see. Keep the D at 1. Increase the P until you see a weird response. Then increase the D a bit. Again, go high on P as much as you can. Like as much as it actually changes the result. You will see that it's not as simple as that. You still need to go up, down, like reduce them. Like you go to thousands and then you realize it's actually increasing. Like you need to go down. Like you go to some numbers, you are like, wow, that's a very bad response. It doesn't look like a system at all. Like it just goes up and down. So it's an experimental process. It's very important to see how tuning works. So when you are doing actual tuning on your robots, you have some understanding of how it will look in reality. Like if the robot suddenly starts doing weird stuff, you have an idea what is happening. Oh, I need to reduce this gain then. So that's what is important here. Let's move on to the next task if you are done. If you want more time, just let me know. So task 2 is about position controller. In task 1, it was about attitude control that directly outputs our angular acceleration, which goes to our control allocation unit and goes to our multirotor. In task 2, we are trying to to write our position control. We are almost writing everything in it. By everything, I mean you need to calculate the attitude, and you need to calculate the output acceleration from the desired position. And at the end, you just need to tune it. So how do we calculate the attitude? The way that we calculate the attitude, given the desired acceleration, in attitude, as I mentioned, we assume that we know the acceleration and we know the yaw. Now we want to calculate the roll and pitch. So if we have acceleration, in order to get the direction of our thrust, the direction that we need to generate forces for, we deduct the gravity from it, so we know the direction of our thrust. So for example, if our desired acceleration is 0, we technically need to generate a thrust in the exact opposite direction of gravity to keep zero gravity, zero acceleration. Otherwise, we will go down. Or if you want to go with 2 meters per square second forward, you still need to generate that gravitational acceleration as well, plus that 2. So that's why we are doing A minus G here. After having the direction of our thrust, desired thrust, we assume that if all our rotors are completely horizontal, we know that our Z direction, if you remember, it was FRD convention, forward, right, down. So our Z direction is in the to the bottom of our multirotor. So if we know what our generated thrust should be, that's exactly the opposite of the direction of our Z axis. So for example, if this is our, if this is your drone, you need to generate this thrust in this way. Your Z would be exact opposite of it. And then we can calculate the X and Y axis. You can see the mathematical formulas there. You just need to write that function in task 2.1 calc attitude. So assuming that you have inputs as acceleration and the desired yaw, you need to calculate the roll pitch yaw. So you have the base code here. Following the task 2, you just go forward like here. You can see all the formulas here. After you have written that, you can actually run this part, and the results that are coming out of it, let me run it here. You will see some results right now. Since it's an empty function, all the results are like 0, 0, 0, 0, 0, 30. But I also provided the expected results, so you can compare if you have written it right or not. So if your function is correct, you will see results similar to these. I think 10 minutes should be more than enough. Let's have 10 minutes for this part. Try to write down the calculation of the attitude from the acceleration. Just an explanation. If you want to access your gravity, like your gravity here is like, you can put a breakpoint on it and see what's the measure, but it's 0, 0, and 9.8 something. Because our Z is downwards in any frame, gravity is at the same exact direction of the down. It's 0, 0, 9.8 something. So that would be your gravity. It's not that important. Just you can use directly this as your G. And you have ACC commanded as your A. So you can calculate the thrust, then calculate Z from the thrust, calculate X, Y. Just use the formulas and you'll be fine. Since I have not provided the way to convert from axis to roll and pitch, I have written it in my screen in case you haven't been able to successfully convert that. Right now, I don't think there's much time to actually go to internet and like look for it. So I just wrote it down for you. Okay, let's try to do it together. I'm going to do it here, and you can compare. You might find my bug, or you may correct your solution. So first of all, we said we need to calculate the direction of our thrust, which just was as simple as the commanded acceleration minus our gravity. So that was the first step. Let me see how it's here. Yeah. So after that, in order to calculate the z-axis, we just want to normalize the opposite direction of the thrust, right? If you remember, it's just minus t over normal of t. So it's minus t over normal of t. A bit more trickier is x. I'm going to break it into two parts, like calculating this matrix here first, and then calculating the whole thing. Let's break it into two parts. We call it x of c. I do the whole part. We were crossing it with the z-axis. Can you make sure? Yeah. And it was a new matrix that it was desired. Yeah. 0. And this is just normalizing it. Also, it should be normalized. I mean, technically, if z is a unit vector, this is definitely a unit vector. So the result is a unit vector. You don't need to normalize, but well, just to be sure, to be safe. So this is our x-axis. And y-axis is just a cross between our z-axis and our x-axis. Right? So let's see if it works. Let's run it again. Yeah, looks like it's correct. Okay, so the next step is calculating the accelerator. Basically, we are going to write the loop of the multiplication part of the PID. It's just this simple formula. How do you write it? You need to calculate the errors, you need to multiply the errors, and update the output. Don't worry about taking care of the limits, taking care of the wind up, integral wind up. It's all taken care of. All you need to do here in task 2_2_calc acceleration, you just need to fill this 4 lines here. I think 10 minutes should be more than enough to read this, like, and to fill it. Okay, let's solve it together. First, we need to calculate the position error. So we do have the desired position and we do have the current position. What's the error? So if you see the inputs, we have the position desired and we have the current position. That will essentially give us the position error. Then we want to calculate the error derivative, which is the derivative of error and error of the derivative. So basically, it's a linear system. It's the same. So it will be our velocity error. We can assume that our desired velocity is 0. So we can just do 0 minus current velocity as our velocity error. Then we need to update our accumulated error in our error integral. Sorry. We have already calculated the position error. We just need to consider how much time we spent. So this is our integral term. That's how much we add to our integral term. And at the end, let's just put everything together. P is for our position error. D is for our velocity error. And I is for our error integral. And we're done. So let's see if we can actually plot anything now. So I'm waiting for it to plot. Oh, it has plotted some stuff. Sorry, I didn't notice I need to go up. Yeah, so with those conservative gains, you can see it is able to track a bit, but it's not that good. There is some oscillation, for example, here on our Y and X. You usually can see that actually on the real drones when the position controller is not very well tuned. Like the drones go left and right a bit, like it's like oscillating. It's around where it's supposed to be, but it's not very well tuned. So now the job is to actually tune it. Let's not spend too much time on it. Also, so you can tune the position controller here. Try to do it as well as you can. One very important thing about it is that if your tuning is super duper well for attitude controller, it means that it can follow the different attitude commands. It can follow that one single attitude command that is in task 1 very well, but it doesn't mean that it can actually follow all kinds of attitude commands. So you may need to go back and reduce those gains if you have very bad responses here. For example, if I go, I don't know, instead of half and 2, if I go 5 and 20, let's see what happens. I don't know. Will something bad happen or not? Let's see. Oh, it cannot follow at all here. And if you go, and if you see roll and pitch and yaw, you will see that probably, I don't see actually that much of a problem, but I don't have what's the result of the calculation. Oh, yeah, from yaw, you can see that even yaw is not following, which means that your attitude gains are too high here. Like, you need to reduce also your attitude gains, and that means that, like, you need to go back to task 1, reduce it, come here, try it, go back, reduce it. In general, tuning is a very tedious task. That's one lesson that you can learn today. That's very important. I don't know if I go like this, what will happen. I just realized my laptop is way slower than my computer, because in my computer it just gives the result like that. Okay. Okay, your response becomes better a bit, but you can see X and Y are not good. It means that technically your roll and pitch are not well tuned, because that's why. And well, of course it's not tuned, because here it's, for me it's the default here. The default 1 and 1, I guess. What is it? Yeah. If I make it 5 and 5, probably it's better. Okay, try to tune it. You still have 2 more minutes. Then we will move on to the last task, which is more exciting. Okay, let's move on to task 3. You can play with it whenever you have time. You can even explore the like the simulator. The simulator that I have written is way more sophisticated than this right now. So this is the result of like weeks ago. Since then, I have worked on it, lots of bug fixes and lots of performance boosts. If you are interested, I will probably share the other simulator that I'm working for my contact inspection project with you on it's on GitHub. Right now it's private, but I will probably share it later. If you want it sooner, I can just share sooner. Let me know. If you want to play with it and see like how it reacts, what it does, like that kind of things. Okay, so as I explained, fully actuated motors, one way of achieving fully actuated motors is tilting our drone in a fixed way. So by in a fixed way, I mean you do not have to we just rotate the arms, we fix it at that angle, and it never changes. For example, the rotors that we have in our lab, we have a normal hexarotor that we have tilted the arms, every other arm to 30 degrees and minus 30 degrees. So I have modeled that exact same multirotor that we have in our air lab here. If you start reading it again, like let's run it. If we define it and visualize it, as you can see, we have sideward angle for it, minus 30 and 30, minus 30, 30, minus 30, and 30 that we can add to our rotors. And it will give us this result. If you click here, open in figure window, you will be able to see it in 3D to see how it looks like. Basically, you can even imagine from this. You don't have to pop it up, but anyway. Then after that, you can define the controller. You can just use the same PID controller, but it needs retuning. Both attitude controller and position controller need tuning. There's one difference. In this specific new drone, technically we can fly in any orientation that we want. Well, theoretically. Let's try to fly it completely horizontally, because this is fully actuated. That's the whole point of having a fully actuated drone, is not to tilt toward the acceleration. So after tuning attitude controller, in this section, you can define the attitude type as completely zero tilt. So if you, this will try to keep your tilt completely at zero at all times. You can even see how your accelerations are distributed. Like it means, I mean, at different acceleration, how much you have horizontal thrust and how much you have vertical thrust. And based on that, you can set our output limits for position controller, which is not as important. You don't have to change those things. You can just learn how it works, and then you can tune your position controller and fly in horizontal, complete orientation. At the end, it will plot your roll, pitch, yaw signal, so you can see how roll, pitch, and yaw are keeping zero while your drone is actually flying toward your desired position. Okay, let's assume this is the last part, and like in 20 minutes we should be done. So let's have 15 minutes for this part, and then we can answer questions, talk about it if there's anything, and we will be done. You can play with this code whenever you want, and again, the more sophisticated version of it is on my GitHub. If somebody needs to actually simulate something, or if you want to go more in depth into analysis of the structure and like actually simulating environment and stuff, just text me. I will share the GitHub repo. Some of it is still not there, but what I mentioned, like I'm still not interacting with the world, but very soon it will be in it. So thanks everyone. If no one has a question, thanks everyone for attending this, and thank you for your questions.